Hello friends, welcome to the Formula Engineering Classroom. And in this lecture, we'll discuss about again, some more about the hydrostatic law and some few numerical problems. So, first of all, I want to tell you one thing. Uh, there are some doubts. Means students are asking about that if in the last lecture, let's suppose if I'm drawing a container here, and in this container there is some kind of fluid. And when we are writing the hydrostatic law, that is P equals to rho g h, and then we know there is, as rho is the fluid property, g is the gravitational acceleration, then p is directly proportional to the height or depth of fluid. Then in last lecture we draw a pressure intensity diagram like that. So let's suppose this height is h here. So this pressure intensity, we can write this is p is equals to, this is rho g h. So the doubt is this: if on this free surface of fluid, as there is atmospheric pressure, why the pressure intensity is zero here? Means we know that is, this is the free surface of fluid, and in this case some atmospheric pressure is here, and that is, we can write that is p atm. Then why we are writing for this layer this intensity is zero? So it's an obvious question. So for this case we can discuss, that is, in this case p equals to rho gh is actually defining the gauge values, as we discussed in our pressure lecture. So again, let I'm discussing here, this is absolute zero line, this is absolute zero pressure line, this is atmospheric pressure, this is p atmospheric, and obviously when we are considering or taking the reference of absolute zero line, that pressure will be absolute pressure, and the pressure above this one is, we are saying this is gauge pressure, this is gauge pressure. So actually in this case, this p equals to rho g h is defining the gauge values in the layers. So obviously when we are taking the atmospheric pressure as a reference, then the gauge value exactly at this layer, that is the topmost layer, will be zero, because here is the reference. So this is zero here. And now when we are moving downward here, the pressure intensity is keeps increasing, as this is defining the gauge values. It is directly proportional to h. So let's suppose if we want to draw the pressure intensity diagram for the absolute pressure, so how can we draw? So let I'm drawing this side here. So we know that it is at this layer the pressure is atmospheric pressure, obvious. Now this atmospheric pressure is same for all layers, because this is completely depending on the atmospheric pressure values. This is not depending on the fluid properties or fluid values. This is completely based on the atmospheric surrounding this fluid. So this is same for all layers. Now this is the gauge pressure distribution within the layer. So this value is actually p atmospheric, this is p atm, this value, and p gauge is actually this one. So we can draw, this is the p gauge at, so this is p gauge, this is p gauge, p gauge. Now obviously this whole length from here to here is actually p absolute. Okay, because P atmospheric plus P gauge means actually in this case this is P atmospheric plus P gauge. We are taking the reference absolute zero line. This value is P absolute. Now obviously in this case at the top layer the absolute pressure is equal to the atmospheric pressure. At the bottommost layer, the absolute pressure is equal to the P atmospheric plus P gauge. And here the P gauge is equal to this one. This is P gauge. So in this case, this law is actually defining, or this pressure intensity diagram is actually for the gauge pressure. Okay, that's why the pressure intensity at this top layer is 0 here. You can also draw the absolute diagram like this. So at the top layer, this is the absolute pressure, and the bottommost layer, this is the absolute pressure line here. So this much, this value is the absolute pressure line, this much. This is the absolute pressure line here. Okay, now so this was the first doubt. Then if we want to calculate the some values of, let we want to solve some numericals. So let's suppose we are considering one numerical here. So there is one question here. So let's suppose we are considering there is one container, and in this container up to this height, that we are saying this height is let 2 meter, is water. That we are saying this is specific weight of water, and above this one let there is some oil. So let we are saying this is 1 meter. Okay, and for this oil, let specific gravity of this oil is let 0.9. This is zero point 0.9, and we know the specific gravity of water is 1. So in this case we want to calculate the gauge pressure at the bottommost layer. So to calculate the gauge pressure at the bottommost layer, first we have to calculate the gauge pressure at the interface of these two fluids, that is water and the oil. So let we are saying this is here the pressure, gauge pressure is that we are saying this is P1. So first we want to calculate the P1. So we know for this height it will look like this one. This is the distribution of pressure within the oil layer. So this is P1. So according to hydrostatic law, we can say that is P1 is equals to rho of oil into G into H of oil. Okay, so here what is rho of oil? So as the specific gravity of oil is given, so we can write that is this is 0.9, that is specific gravity, into the density of standard fluid, that is water, that is 1000. G is 9.81, and height of the oil is actually 1 meter. So this is 1 meter. So this value will be equals to, let me calculate this value. This is 0.9 into 1000 into 9.81 into 1. So this value is 8829. This value is 8829 Newton per meter square, because this is pressure, or we can write Pascal. So this is this pressure intensity. So this value is equals to 8829 Pascal. Okay, now this pressure intensity that is due to the oil, so we can consider this is above the water layer. It is like that the air above this water. So as this P atmospheric is remains constant throughout the layer due to air, similarly this oil pressure intensity remains same throughout this layer, that is equals to this P1. So this will look like this one. This is, so this value is P1. So what about the water? So for the water we can draw like this. So this value is P1. Let we are saying this value is P2. This value is P2 and this is only due to water. Okay, so we can calculate here. So we can write P2 is equals to, this is rho of water into G into H of water. So rho of water is, sorry, this is 1000 and G is 9.81 and H of water here is 2 meter. So this is 2 meter. So this value will be equals to, so we can write this is 9810 into 2. This value is equals to 19620. This is 19620. Let me check again. This is 9810 into 2. This is 19620. Okay, so this is also Pascal. So this P2 is actually the gauge pressure due to water only, and this P1 is the gauge pressure due to oil only. So at the bottom of this container, the total gauge pressure, this is from here to here. So actually this gauge, that is P at the bottom, will be equals to the sum of this one, that is P1 plus P2. So P at the bottom is equals to P1. P1 is equals to 8829 plus P2, that is 19620, and that is equals to plus 8829 will be equals to, it's 28449. It's 28449 Pascal. Okay, and this value is actually gauge value, because we are not adding the atmospheric pressure value in this one. So through this hydrostatic law we can easily calculate how much pressure the fluid is exerting over the bottom of the container and all these things. Let if we want to calculate what is the absolute pressure exerted at the bottom of the container, then in that case we can also draw here. This pressure is actually atmospheric pressure. This is PATM, and by standard values we can take it. This is 101,325 Pascal. This is the standard value. We are taking 101,325 Pascal. So for this case, as we draw this diagram, there is pressure, atmospheric pressure remains same throughout the all layers. So this remains throughout the all layers same. This remains same throughout the all layers. So here this is the atmospheric pressure and this is the gauge pressure. So we can write, I'm using this space here, that is P absolute at the bottom is equals to P atmospheric plus P gauge at the bottom. So this will be equals to, this is 101,325 plus 28449. So this value is equals to, so we can add this one, so plus 101,325. So this is equals to 129,774 Pascal, and this pressure is absolute pressure at the bottom. Okay, so now we want to calculate how much force exerted by the gauge pressure due to the fluid on the bottom of the container. So obviously in this case we require the area of the bottom. So let's suppose we are saying that is area of bottom is let 0.2 meter square. Okay, this is the area of bottom, and we want to calculate the force exerted by the gauge pressure. Actually this is the gauge pressure on the bottom of the container. So let again I'm drawing here container, and up to this height is the water, and sorry, this is oil. So the pressure variation is like that. This is P1 over here we are considering, and then this is same throughout here, and this is due to the water, and this is P2. This is P2 and this is P1 actually. Okay, so this value is P1. So now at this corner, this is the gauge pressure, that is P1 plus P2. This is P1 plus P2. Now from the Pascal's law we know that is in a static fluid at a point the pressure intensity remains same in all directions. So obviously in this case the pressure intensity in this direction and pressure intensity in this direction will be same. This value remains same according to Pascal's law. This pressure intensity remains same in all directions according to the Pascal's law. Now as this over this bottom layer the fluid height is same, so according to hydrostatic law the pressure intensity remains same because H is same. So this value throughout the bottom remains same. And again at this corner according to Pascal's law, this is the pressure intensity, and this pressure intensity and this pressure intensity is same, and sorry, so this is the distribution of pressure around this container due to this fluid. So the pressure intensity at the bottom, that is the gauge pressure, is equal to P1 plus P2, and we calculated the pressure gauge pressure at the bottom. Oh sorry, this is M. Gauge pressure at the bottom is equal to 2849 Pascal. So as I want to calculate the force exerted by this fluid, that is due to the gauge pressure at the bottom of this container, so we can directly multiply this gauge pressure to this area, and we can multiply this gauge pressure to this area because in this case the pressure distribution is uniform throughout the bottom here. We can't do if this pressure variation is not same, means if this is variable over this area, in that case we can't multiply directly the pressure intensity to the area. In that case we have to take the average pressure intensity that is exerted by the fluid on the bottom of the container. But in this case, as we can see, the pressure intensity at the bottom is throughout same. We can directly multiply this pressure intensity to the area. The force at the bottom to the gauge pressure, we can write the P gauge at the bottom into the area. So here P gauge is equals to, it's a 28449, and the area here is, this is 0.2 meter. This is 0.2 meter. So by calculating this one, we can write, so this is 28449 into 0.2. So this is equals to 56898. So this is 56898 Newton. So this is the force exerted by this fluid on the bottom of this container. Oh, sorry, actually this value is not 56898, it will be 5689.8. There is a point 8 here. Okay, so I think this is clear. That is, we have to directly multiply the pressure intensity to this area when the pressure intensity is uniform throughout the bottom. In this case, this is uniform, so we can directly multiply it. But when this is not uniform and this is variable, when the pressure intensity is at this corner and over this layer is different, in that case we have to take the average value of the pressure intensity, and that average value of pressure intensity we have to multiply this area, that is 0.2 meter square. Okay, now we are extending this problem, and again we are taking our container here, and we are attaching a tube here. Okay, is the case. Now the water in our case is maintaining, that is 2 meter of height. This is maintaining 2 meter of height. This is 2 meter, and remaining is an oil, and let this is 1 meter. We are saying this is 1 meter, so this is an oil and of specific gravity 0.9. Okay, this is actually 0.9, it's not G actually, this is 0.9. Now the specific gravity of water is 1. And now in this case we want to calculate actually what is the height rise of water in this tube, because this fluid is the downside, because this is heavier and the oil is lighter one. So this water will rise in this tube, and we want to calculate what is the height it will gain in this tube. Let us suppose, if I'm saying this is, let h dash, this is h dash, height of water in this tube. So how can we calculate in this case? So obviously in this case, in the container there is oil and there is water, but in this tube there is only water. So according to our calculation, we know that is at the bottom the pressure intensity due to the only gauge pressure at the bottom of this container is actually 28449 Pascal, and as it's maintaining the same layer, the pressure intensity will remain same. So means the pressure intensity in this container and the pressure intensity in this tube will be same. So means the pressure intensity at here and here will be same, but in the container there is an oil and water, but in the tube there is only water. So we know at the same layer the pressure intensity will be same. So we know that is here the pressure intensity is, let if I'm saying this is P gauge, at the bottom is 28449 Pascal. Okay, and this pressure intensity is also here, but this pressure is only maintained by the water. So we want to calculate the height of water in this tube. So simply, as we know the pressure, in that case we can directly equate this pressure exerted by the water in this tube. So we can say that there is 28449 pressure will be exerted by the rho into G into H dash of water in the tube here, because this pressure intensity is only maintained by this water here. So by this calculation we can write this is 28449, and the row of water is, we know, that is 1000. G is 9.81, and we want to calculate H dash water. So let me calculate. So H dash water in this case will be, so this is 28449 divided by, this is 9810. So this will be equals to 2.9 meter, and actually this 2.9 meter is only due to water. So this pressure intensity, that is 28449, is maintained by water by maintaining the height of 2.9 meter of water. So you can see here at the bottom the same pressure intensity, that is 28449, is maintained by the 2 meter height of water and 1 meter height of oil. But in the tube the same pressure intensity, that is 28449, is only maintained by water by 2.9 meter of water, and here the total height is 3 meter. It is obvious because the oil is the lighter fluid, and it is lighter fluid, that's why it will take more height to maintain the same pressure. But as the water is the heavier fluid, it will take less height to maintain the same pressure. That's why it is only taking 2.9 meter of water. And this is how the hydrostatic law works. I think the concepts are clear in this case. In the next lecture we will discuss about more and some paradox of hydrostatic law. Thanks for watching. Take care of yourself.